Okay, so let's start. Today we're going to talk about inner product and norm. And if you're lucky, we're going to talk about matrices as well. And we'll finish the linear algebra review. But if the morning session is any indicator, we're not going to be as lucky, but we'll see how it goes today. So the first thing that we talk about is the inner product. The idea of inner product. How many people have heard about inner product? 1, 2, 3. So what is an inner product then? Okay, 3, 4. Definition is up there, but yes. Anyway.
Is it cross product?
It's not cross product, dot product.
Yes.
Yeah, so another name is dot product. So the idea is like simple. So if you have two vectors in Rn, let's say x is, I'm going to write it as a column vector, and then y is y1 up to yn. So it's a scalar that you associate to any pair of vectors, x and y. So we have this definition. So you basically sum the xi, yi pair. So you multiply xi by yi, each coordinate by the corresponding coordinate, and then you sum them. If you view, the vectors as these n by 1 matrices, as we are doing here, then you can write this as x transpose times y. Okay, so 1 by n times n by 1 is a matrix product, and it would give you the same expression. Okay? So it's scalar, so really it's x transpose y, or this expression, and we also use this notation, angled brackets, and that's the definition of the inner product. Okay. To every pair of vectors is associated with scalar. Once we have this, we can define something called a norm, or length of a vector, basically. Okay, so how do we define that? Basically, you can take the inner product of a vector with itself, and then take the square root, and that would define the norm. And you can see that it would be like the square root of xi squared. So you raise every coordinate to a power, and then sum, and then take the square root. So what does this mean? For example, if we have a vector, let's say I have like a vector 1, and then 2 here. And then vectors are often, we represent them either as arrows starting at the origin, or we could do, think of them as points, really, 2 different viewpoints. So let's say look at it as a vector here from starting at the origin. So what is the length of this vector, let's say? You want to compute the length. Anyone?
Is it norm?
It's the norm, yeah, but just if you don't know about the norm, how do you compute it? Just like a triangle, we can think of it as 1 and then 2 here, Pythagorean theorem, right? So what is the norm? Oh, what is the length?
1 squared plus 1 squared squared.
1 squared plus
1 squared. Or 2 squared.
2 squared, yeah. And then you take the square root, that would be the hypotenuse, something like that. So that would be 5, root 5. And this is exactly the definition of the norm. If you imagine x is like, here would be 1, 2. Okay, so if you compare with the definition, it matches the way you compute the length, and it generalizes to many dimensions. Yes?
I'm not sure if this is correct, but is the inner product between the transpose and the non-transpose the same like the square root?
Are you talking about?
Transpose times x is the same with the square distance.
This is the same as the norm square.
Yeah.
Yes. That's the definition of the norm. Yes. Because the definition is just the square. You take the square root. That's by definition the norm of x. Okay. So the norm tells you something about the length, or actually the length of the vector. Okay. And then once I have the length, I can define distances between two vectors or 2 points, actually. Distances between 2 points. For example, if I have, let's say, these two vectors, x and y, and I want to, here you're going to view them as basically the points. Most of the time you're thinking things as points. So these are the 2 points in R2, and I want to measure their distance, which is this, the length of that line. You can view this as the norm of a particular vector. So for example, so this would be, what is this vector that goes from, rather I should do. Anyone knows what this vector is? If x and y are given like that, what's that vector? Yeah. Who's we? Yeah.
Y minus.
So this would be y minus x. Yes, because if I add x to this, I get y. So x added to this would give me y. Like if you remember what in picture vector addition looks like. And so the length of this would be what I want, would be the distance. So the length of this, y minus x is or I could do x minus y because the sign doesn't matter. So the length of x minus y, or the norm of x minus y, is the distance between the 2 points. So you have 2 points x and y in Rn. You can measure the distance as the norm of the difference. Okay, and this is by definition. You can write it in terms of the coordinates, root of the sum of the difference squared. Sounds good? Right. So once you have the inner product, from the inner product, you can define the norm. From the norm, you can define the distance between points. What else we can define using an inner product? So these are geometric quantities, okay? So this gives me an algebraic way of computing the inner product. Once I have it, I get geometric information, length and distances. What else we can get? Yeah.
Projections.
Projections, okay, projections, we'll get to it, yes. Projections is really the top thing that we want to, but yeah.
Agreement between two vectors.
Agreement between two vectors, yeah. So if the distance is 0, like the norm of the difference is 0, then they're going to be agreed. But there is something else that, yeah. Orthogonality, okay, so we're getting close. So in general, what we can get is the angle, okay, an angle between two vectors. And if the angle is 90 degrees, they're going to be orthogonal. But that's what we care about. But let me just point out this more generally. So if I form like this quantity, the inner product divided by the norm of x times the norm of y, anyone knows what this kind of quantity would be? Yes.
Cosine thing.
Okay, so
Cosine theta.
cosine theta, okay, yeah, both of them correct. Cosine of theta, theta being the, let's say, angle between x and y. So if we have x and y here, if the angle is theta, so this quantity, the product, the inner product divided by the product of the norms, this is going to be always between -1 and 1 by a very famous inequality. Anyone knows yes, Cauchy-Schwarz, yes. So Cauchy-Schwarz, if I spell it correctly, maybe not. We'll check. And so it can be the cosine of something, and you can either define the angle between two vectors as the arc cosine. So the angle is given by the cosine of the angle is given by this. So you take the arc cosine, you get the angle, and it matches your intuition in R2 and R3. Okay. And in general, you can take it as the definition of the angle. Okay. Between two vectors. And so once we have the notion of an angle, it's a geometric thing. We can talk about like orthogonality. So orthogonality means the angle is 90 degrees. Okay. So what happens if the angle is 90 degrees from this? Yes.
Inner product 0.
Inner product 0. So angle 90 degrees This means that the cosine is 0, right? So you say that x is perpendicular or orthogonal to y if and only if, let's say, that angle, let's write it as angle x and y is 90 degrees or pi over 2 if you want, which is the same as xy being equal to 0. Okay, so we can say two vectors are orthogonal if and only if the inner product is 0, because this quantity would be 0 if and only if the numerator is 0. Okay. Sounds good. So you have a notion of orthogonal vectors. So can you give me an example of two orthogonal vectors, maybe in R2? Yes, maybe let's try someone else, but if not, anyone else awake? So what's your name? Yeah.
0, 1, and 1, 0.
Okay, good. What's your name?
Ashmit.
Ashmit. And what's your name?
Jordan.
Jordan. Okay. If you keep answering, I'll learn your name. If you just answer once, I so answer more. 1001. 10. So this is one vector. This is the other one. So 0, 1, 1, 0. And then you can see that the inner product is really 0. It's obvious, but so geometrically they're orthogonal, and then you can verify algebraically. Okay, just multiply them. You get, sorry, the other way around. You get 0 times 1 plus 1 times 0. It's 0. Okay, it's linear algebra because you can do this algebraically and tells you something about geometry. Yes.
I missed something. What's the between the if and only if the angle between x, y, what's that equal to?
Oh, pi over 2, or like 90 degrees if you want, 90 degrees. Okay. So far, so good. Hopefully, you knew the stuff before. Right? Questions? Okay, inner product gives us norm and distances and angles and the notional orthogonality. Okay. So there's also this identity that if you square then the distance of x minus y, sorry, the norm of x minus y squared is the norm of x squared plus norm of y squared minus 2 times xy times here the inner product. So this is like the identity that you know for scalars. A squared plus b squared minus 2ab. A plus b squared is equal to that, but this you can prove by just, let's say, writing this as this, expanding it as a definition, x minus y transpose times x minus y, and then do basically expand and simplify. Okay, so this identity would be useful for us later. For example, if the two vectors are orthogonal, what would happen is that x inner product y would be 0. So you get the Pythagorean theorem. This would be Pythagorean. So inner product is 0 implies norm xy squared is. So you would prove the Pythagorean theorem rather easily. Okay. Okay. The next thing is, once we have the notion of orthogonality, just point 1 here, of two vectors, I can extend to the notion of orthogonality to a subspace. So if I have a vector x in a subspace, so here subspace would be linear. I didn't explicitly mention what a linear subspace is, but hopefully you know most of our subspaces are, almost all are linear. So we have a linear subspace V in Rn, and capital V, and we have another vector, x. So you say that x is perpendicular to V, or perp V, or orthogonal to V if x is perpendicular to every vector in V. So this thing that I wrote there. X perpendicular to V for every V in V. Okay. And the idea of an orthogonal complement, which is written as V perp, is the set of all X that satisfy this, that are orthogonal to V. So this is really the set of all X such that X is orthogonal to V. Okay, so let's see what it means. Let's consider a subspace which is going to be like the xy plane in R3. Let me do it in the middle here. So we have our subspace here. So that's xy plane. So V is the xy plane. I can write it as alpha, beta, let's say 0, such that alpha and beta in R. Okay. So anything in R3 that has the last coordinate 0, but the other coordinates are kind of arbitrary is in the xy plane. Yes.
What you said that's a property of the linear subspace, but you didn't.
No, I didn't talk about properties of linear subspace.
So what is a linear subspace?
What is a linear subspace? Anyone wants to clarify? What is a linear subspace? You have taken linear algebra. You should know what a linear subspace is. Forgotten. Yes.
So like contains zero vector is closed under the scale multiplication dimension.
Great. So a linear subspace is a subset of the bigger space. Okay. The bigger space is a linear space, like a vector space. And so a subspace is called linear if it contains 0 and it's closed under scalar multiplication and vector addition. So if two vectors are in the same set, then the vector addition will be in the same set. Okay, and if you have a vector in that set, if you scale it, it remains in that set. Okay, and these are like in, let's say in R3, they look like lines and planes and the entire space. They all have to pass through the origin. Okay, so here, for example, is a linear subspace. So what was your name, by the way? Stanley, okay. Stanley, Jordan, okay. And then your name was?
Ashmit.
Ashmit, okay. So far, 3. Yeah. More people, when you answer, you can also name yourself. So where were we? Okay, so we have the xy plane. So can you give me a vector which is orthogonal to this? So this is a linear subspace. You can verify. If you have two vectors in the plane, then if you add them up, they remain in the plane. They're not going to come out. And if you have a vector in there, if you scale it, it's going to remain. And it passes through the origin. So what is the vector that's orthogonal to this? Can you give me, yeah,
Like z-axis.
louder?
Z-axis.
Z,
Or like the.
oh, z-axis.
Yeah.
Okay. Yeah, okay, 0, 0, 1 is going to be perpendicular to V. And in fact, as you mentioned, anything on the z-axis would be, right? Anything on the line that kind of, anything that lives on this line, right? A different color. So any vector, like, doesn't matter which way you go, right? It's going to be orthogonal. The reason is easy because the two first coordinates would be 0 and the last coordinate on this one is 0. So when you take the inner product, so I get, for example, 0, 0, 1, inner product with alpha, beta, 0 would be like 0 alpha plus 0 beta plus 1, 0 would be 0. Right? You can take the inner product, you can see that the inner product would be always 0. Okay? So this is perpendicular. So any other vector that is perpendicular other than this, or orthogonal to V? Anything else? Yeah.
Vector with the first entry being negative beta, second entry has alpha, and the third entry is
Whatever else.
0.
Gamma. So this vector is orthogonal to this particular one, right? But it's not orthogonal to V, right? So this alpha and beta, this is like a particular set of numbers, right? So when I write something like this, these are dummy variables. So if I pick, I mean, this is not like a well-defined vector. So you have to plug in beta, alpha, and gamma. And if you plug it in, it's going to be orthogonal to one of these vectors, but not all of them. Okay, so this will rule out. Okay, does that make sense? Yes.
The 0 vector?
The 0 vector, yes. That's also, you can think of it as on this axis. That's true. 0 vector is always orthogonal to everything else. The 0 vector is going to be in the orthogonal complement of any subspace. So anything else? I would take no as an answer as well. No is a well-defined answer. So in this case, there's no other vector. Okay? So this z-axis will be V perp. This is the set of all vectors that are orthogonal to V. Okay? Sounds good. That's the notion of orthogonal complement. To every subspace there exists a complement. It doesn't have to be this xy plane. It can be a different plane. I gave another example in the morning session. I'll probably post the video if it turns out. So for example, it could be like the plane that just passes through the z-axis, but has both coordinates x and y the same. Okay. This is just easier to work with. For every linear subspace, there exists a corresponding V perp. So what is the orthogonal complement of V perp? So this turns out to be also a linear subspace of itself, like in itself. Let's say this is W, some other linear subspace. We can verify that it satisfies the axioms of linear subspace. So what is the perp of that? What is the orthogonal complement of that? V. Who said that? Okay, what's your name?
Alfred. Alfred,
Alfred. Okay. Alfred. Okay. So the correct V is going to be the so kind of if you reason about it, once you figure out that this every vector here is going to be orthogonal to V, then of course every vector in V is going to be orthogonal to that, and that those are the only ones. You have to argue that, and so W perp is going to be V. Okay. So this gives us the identity is in general true. V perp gives you back V. So if you take perp twice, you get back the same thing. So there's really duality. You can't generate infinitely many subspaces this way. Just start from one, you get another one, and then back to this first one. So there is a duality relation. Sounds good? Okay. Yes.
So if the subspace is R3, then its orthogonal complement is just a 0 vector?
That's a good question. So did anyone, I'm going to repeat the question. If the subspace is R3, is the orthogonal complement just a 0 vector? Yes. Anyone else? No? Yes. Yes. You agree or disagree? Disagree? So why? There could be higher dimensions. Okay, so this is to clarify, when we have to specify the ambient space, let's say, okay? So R3, if it's the ambient space, that's the whole thing. So basically, okay, it's a good thing. So you're taking the orthogonal complement relative to an ambient space. Okay, when we say like if R3, if you think of it as a subspace of a bigger space, then it's no longer the ambient space. Then yes, it could have a orthogonal complement in a bigger space. But let's say if I restrict myself to Rn as the ambient space, if V is equal to Rn, then so if Rn like is V in this, then V perp would be that. If Rn is the ambient space, or basically we have to fix what the space we're in. Okay, then it's true. There's no other dimension to go. Does that make sense? Yes. Both good points. Okay, and then something else we notice here is that the dimension of V plus the dimension of V perp turns out to be n, like the dimension of this space. So this is 2, this is 1, and add up to 3. In the other case, it's also the same. So this would be like dimension of V would be here n plus V perp would be 0, you get equal to n. And this is in general true. The dimensions of V and V perp add up to the dimension of the whole space. Any other questions? Here's another example which we can skip. So if you have X, for example, as a matrix, if you remember this image of X or the column space of X is just the span of the columns that defines a linear space, linear subspace. And anyone knows what that image is or the linear subspace is? So what is this? What is V itself? Yes.
Something similar to like 1 0 0 0 1 0 because the ones one could be added, and then the 1 and -1 make it like, but the bottom is 0, always 0. So the columns don't add up to bottom 0.
I understood the last part, but what was the first half? So what I'm asking is, what is this space, right? So can you say that again? Like,
The space would be like the first two elements of the column, but like it'd be like similar to like a plane.
Okay, what plane would that be?
A plane with like the third value being 0.
The plane, the third value being 0, and the first two could be, let's say, anything.
Yeah.
So what is that? Like in R3 it would be
It's like the
just exactly the V that we did. Okay, so this is just the same V, it's just you're just specifying a different basis for it, basically. So what ends up happening is the V perp is going to be exactly the same thing to the Z-axis. So it doesn't matter which basis function you pick. The V is defined once you specify a basis, you define the V, and then the V perp is defined based on V itself. Yes.
But the X values doesn't necessarily say like it's X, Y, or Z, or we just
Right. Okay. So what I'm saying is like yeah. What when I say X, Y, Z is just to be referring to. You can say X1, X2, X3.
yeah, I know it's like the axis.
No, the dimension would be 3 because it's like
But
three.
I mean the axis.
Yes, that's not important. Yeah. Don't worry about it. Just it's a plane. It's a coordinate plane. Yes. If you want to precise, you have to specify what X and Y and Z is. Yes. Yeah.
This is because the span of those two columns is the XY thing.
Yes. Yes. So the subspace, once you specify it, then that defines the equatorial couple. Yes.
Is the V perp equivalent to the kernel of X?
Sorry?
Is the V perp equivalent to the kernel of X?
Okay. Is V perp equivalent to kernel of X? What do you think, guys? I see something like this. Anyone nods vertically? Is it or who thinks? How many people think it's the truth? How many people? At least one, maybe. How many people think it's not true? Okay, 2. We should be sure one of you wanna. Why not? Why?
The kernel asks. Oh.
Yes.
I was thinking like if you had vector that wasn't perfectly orthogonal, but it still had direction in the axis, and to apply the matrix on it would still go to 1. Never mind.
Yeah, there is a very easy answer to this. So if you remember the definition of the kernel. Yes.
I thought it's true.
So where does the kernel live? Like in this case. What, like it's a subspace of what space? Yeah.
Space.
Kernel is the null space, but that's just the renaming of it. So where does it live? Like R2, R3, R4, R5, R1, R.
And then the V vector is defined.
V, so let's see, V, where does V live? Okay, let me yeah.
I think also orthogonal complement is like living inside X transpose, so the kernel of X transpose.
Orthogonal complement is living in the kernel of. You're close, but let's parse this a little bit more. Yeah.
The kernel of X is in R2 and V perp is in R3.
Okay, good. The kernel is in the input space. The kernel of X lives in R2 because this is 3 by 2. Okay, so if you remember, X maps R2 to R3. It's an operator that takes vectors in R2, maps them to R3. And so the kernel is everything in the input space that goes to 0. So it has to live in R2. V is the image, V perp would be in the same space. So both V and V perp live in R3. So this can't be true. Can't be true because they live in different spaces. So what was your name, by the way?
Aiden.
Aiden?
Yes.
M with the M?
Yeah.
M?
Yeah.
Okay, Aiden, okay. But there is something very closely related, which is true. So if you put that answer, somehow massage it a little bit, how can you fix this? So image perp is equal to kernel of something. Anyone? X transpose. Yeah, this is the fundamental relation. So X transpose would be 2 by 3. So X transpose would map from R3 to R2. So it would be like 1, 1, 0, 1, negative 1, 0. So the kernel of it lives in R3. So at least it can be a candidate. And you can actually prove that this is true. And this is one of the fundamental relations that actually you're going to need. This is what kind of allows us to do kind of regression. Okay. It's a very good point. Okay. So think about this a little bit, and by the end of this course, hopefully this will become very clear. Sounds good? Good? Okay. Any questions? I haven't proved this. You're welcome to try to prove it yourself, but at some point we're gonna see it. Just make sure that you understand the kernel and the image are in different spaces in general. So let's move on from this example. Okay, let's try to prove or actually do projection. So how many people have seen projection or power projection? 1, 2, 3, okay, bunch of people. So what is orthogonal projection? Let me not show it. Anyone? So we have a vector and we have a subspace. So subspace V in Rn and then a vector in Rn. We want to project the vector onto the subspace. How do you define this object? Yes.
If you make a matrix like A, I feel like they can cross product with the two segments.
Make a matrix. How do I make a matrix? That sounds too complicated. So V is like an abstract subspace. So there's no matrix here. You have to construct a matrix if you want. We can do that. But I'm looking for like a simple definition. What does it mean? Project X onto. Yes. All right. Yeah, go ahead. You go ahead first.
Find where the vector X or a vector in V that's orthogonal to that.
A vector in V that's orthogonal. This is close.
Vector orthogonal to X. Then
So we have V. let's say I have a subspace V here. Right, and then I have X here. Okay, we are looking for a vector in V, that's going to be a projection, such that, yes,
A vector is closest to X and it's like a component maybe of X.
that's the first one is great. So the vector in V, which is closest to X, is the projection. Okay, so we are looking for a vector in V, which is closest to X. Okay, that's a very good definition. So I'm going to find a vector here such that the distance between X hat, let's call this X hat, and X is the closest among all the vectors in V. So for example, if I take another vector here, maybe that, then the distance would be just, let's say this is Z, the distance would be X minus Z. This is going to be bigger than the distance between X minus X hat for any Z that, any other Z, okay? So you vary, like you pick a vector Z in R in V, and then you vary it and look at the distance of the Z to, or like these points. Basically, we're looking at the points. So think of the point here and this point. So this distance, you look at it and then vary Z. And when this distance becomes minimum, that's where that point would be the projection of X. Okay. So this is the smallest. The other things are larger. So for example, if you take another Z here, that would be the distance. It's not obvious here, but this one is going to be assuming that, I mean, there's a property that has to satisfy. Does that make sense? The vector in V is closest. So like we write it like this. Pick a Z in V and look at the distance of X to Z, which is the norm of X minus Z. And we then take the argmean over all Z in V. So argmean means minimize the function. So if the function is, we have a function, so fix X, and we have a function of Z. So you minimize this over Z, and the argument that minimizes is called the argmean. Okay. So minimize F and take the minimizer. This is going to be argmean Fz as Z varies in V over, so we minimize over Z, over V. Right, this is fine, over V. Okay, it's an optimization problem basically. You optimize, minimize a particular function, which is the distance to the subspace, distance of the vector to the subspace, and the minimizer, whatever minimizes it, I'm going to represent with X hat. Okay. The intuition is that it's the best approximation I have to X from the elements of V. Okay, if you think of this distance as information loss, let's say V is my knowledge, and this vector is not in my knowledge, but I want to find the closest in my knowledge to it. That's projection. And this difference is going to be the error. So what we have here is like X minus X hat. This I'm going to call E. So generally we'd have, when you project, you would have this thing which is like the error. So X hat, and this would be the E, which is X minus X hat. So this would be my error, and I can also maybe do it here if you want. It's just starting from the same origin. This has a particular property. What property does it have? Which is uniquely characterizing projection. Yes.
It's a cosine.
Cosine? This is a vector. It can't be a cosine. It,
If the inner product of the divide by one, it's
take the inner product of what? By what?
the X and V. Correct.
I can't take the inner product of X and V because one is a vector and the other is, you have to define what it means to take the inner product of a vector and V. There's an easier answer, yes.
Inner product is E and X hat are equal 0.
Inner product of E and X hat is 0. This is true. But this is not enough to define the projection. There's more. E is orthogonal to more. Yes.
Here's one.
E is orthogonal to V. What's your name, by the way? Tina, okay. E is going to be orthogonal to any vector in V, including X hat. Okay. If you have a vector X hat such that this error is orthogonal to V, then that should be the projection. Like intuitively it's clear. So the distance is minimized when the error is orthogonal to V, and you can prove this. So this is the defining characteristic of the projection, orthogonal projection. You have the vector, and you drop the endpoint perpendicular to, so just, it's as if you shine a light atop, just perpendicular, you just drop. That would give you, the endpoint would give you the projection. So any other thing you can just prove. So basically the error x minus x hat satisfies this. So the projection is uniquely characterized. It's the only vector that has this property. Yes.
The question, I think it's a good one, but does this mean that X and B have to be on different R's?
Different.
Different R's, so that X has to be maybe on the Z, has a Z component, and then V is a subspace only on the two-dimension R2.
No. So I mean, this picture is like for convenience. So any subspace, so it could be like the subspace could be like this in R3. Okay, and the vector could be even on it, or it could be off it, or it could be like in any direction. So for any pairs of subspaces, any vectors, you can define this. I'm just doing it like this because it's easier to see. Okay. Right. Yes.
Show the pen be on the subspace. In that case, what would be the orthogonal? Would it be like, would there be no orthogonal vector?
You tell me. So
Like this.
so I have this subspace V.
Oh, see the screen.
Okay. Let's try again. So this is V, and then I have a vector which is in there. So what will be the projection? There. I heard something. Louder?
Just X.
You said it? Louder? Who? Oh,
Just X.
X. So a new person. So what's your name? Luke. Okay. So it's just X. Why? What is the error? So the claim is that X hat would be X. So the error is 0. 0 is orthogonal to every possible vector, including V. And I said that this is the characteristic definition, like the characteristic property. If you find a vector in V such that the difference is orthogonal to V, then it has to be projection. The X has to be projection. Okay. And it's also clear, it's the closest vector to any vector is itself. You don't even need projection like that orthogonality. It's well defined. So for any vector and any subspace, there is a projection, and it's actually unique. There's a unique projection. So the next thing that I want to note is once I have this property, then I can write it, rewrite it as this equation as x is equal to x hat plus e. This is just rearranging this definition. And it happens that by definition, this is in V, and we also know that now this V, the E is in V perp. Because E is orthogonal to V, it has to belong to V perp. Okay, so now I have a nice decomposition of a vector into two components, one in V and one in V perp. And because every vector has a projection, unique projection on any subspace, if I specify a subspace, I get this decomposition for every vector in this space. Okay, so like fix a subspace V, it decomposes the space into two pieces. One component which is in for every vector, there's one component which is in V and one is which in V perp, and they're orthogonal to each other. So x hat, as we have seen, is orthogonal to E. So it's an orthogonal decomposition of the space. So for example, if you have like V is the xy plane as we had, alpha beta 0, alpha beta in R, then if I have a general vector like x1, x2, x3, that's my x, then I can write it as a projection onto the xy plane, which should be kind of clear that it's this, plus the error, which is going to be this. Again, this is for convenience because in this case, for the xy plane, I can just write things out. So when you project to the xy plane, you just zero out the z coordinate. So this would be x hat. This would be, and it works for any vector. But this is not limited to the xy plane. For any subspace, it works. And it would give you some non-trivial decomposition. Okay. Sounds good? So this fact is written like this. So you write like Rn is decomposed into V plus V perp. And they use this notation, like a plus with a circle. What it means is exactly what I mentioned. Every vector in X can be written as the sum of two elements, one in V and one in V perp. It's a decomposition of the space in this fashion, and the two components are going to be orthogonal. Okay, so that's kind of summarized in this proposition. For every vector X in Rn, we can uniquely decompose it as X hat, like a component in V, which is going to be the projection of X, and a component in V perp, which is going to be the error. And if you think about it, you can also view it differently. So you can think of E as the projection of X onto V perp, and X hat as the error of that projection. There's this dual. I'm not going to dwell on that point. And this is mnemonically written like this, and sometimes they call this symbol the orthogonal direct sum, or direct sum of two subspaces. We're not going to use it much, but if you end up looking at it like in more advanced linear algebra book, you might see this notation. This is the meaning would be used. Okay, so like if this idea of projection allows me to do orthogonal decomposition of the space. So for example, I mean this in this case, we are decomposing the space into this plane and the x-axis. Every vector has a component which is on the plane plus a component which is on the z-axis, and the sum to give you the original vector. This picture, you can just arrange it in any way you want, like rotate it, and if it's true as well. Okay, any questions about this? Let me stop here. Let's stop here. Questions? This kind of clear? We're going to summarize it. So we'll see. I mean, this is a preview. Later you'd see. For us in regression, you have a design matrix. The column span will define a subspace, as we have seen. The column span or image, I should write it as image. And then the projection is actually the vector fitted values. And E would be the residuals. So exactly. So that's the geometric picture to remember. So for every vector X, I have this kind of basically geometric picture. We project V X onto V, you get X hat, and the error is orthogonal to V. Or you can think of the projection of the shadow if you shine a light on top onto V, and the errors kind of is perpendicular to the subspace as well as the length is the shortest path. Or like the length that it's just the shortest path, let's say. Okay. And here's the proof, which I'm going to skip. It's optional. You're welcome to look at it. This proves that the projection is unique and the error is orthogonal, because we define the projection via the shortest length, because you have to prove it that the error is orthogonal, and if and only if, like if the error is orthogonal, then x hat is the projection, and conversely, if x hat is the projection, then E is orthogonal. There are two sides to it. Okay, so we're almost done with the projection. So to summarize, the first point we have already seen, so Rn can be decomposed into V and like direct sum of V and V perp. So if you, like all the things we discussed, is like compactly like summarized in this like equation. So if you look at it and understand it, then you understand the projection, then orthogonal complements and the relation so far. This one I mentioned before, the dimension of V plus dimension of V perp is equal to n. We haven't formally proved it, but it's true. And this one we also discussed V perp. If you take perp twice, you get back V. This one, interestingly, you discovered yourself, kind of remember. Image of X perp is equal to kernel of X transpose. This is very crucial to us, but we're going to see it later. Okay. It roughly says that orthogonal to every column of, if a vector is orthogonal to every column of X, because if you're orthogonal to, so the orthogonal complement of the image, so the image of X is the span of the columns. So to be orthogonal to the image, you have to, it's equivalent to be orthogonal to every column. That's enough and sufficient, like necessary and sufficient. So being orthogonal to every column means that you are in the null space of the X transpose. This is, we'll see. And then a consequence of these two facts, let's say call this A, call this B, is that the rank of X plus the nullity of X transpose is n, because this is really the dimension of the image of X, and this is the dimension of the kernel of X transpose. And because the two subspaces are orthogonal complement, the dimensions add up to n. Okay, so put A and B together, you get this rank nullity result, which is useful, but it's not. That's, you're not gonna dwell too much on it. So the only thing that needs like a formal proof, I mean, I really didn't prove this one and the other one, but we're not gonna use it. The first one I proved, not, actually not proved, but we spent a lot of time on it. The B is gonna be, we're gonna prove it later. And like in the context of regression, at least this course. Any questions? So that's the summary of the ideas of projections. So linear, like inner products, norms, distances, and then orthogonality, orthogonal complement, this all summarized like in this kind of fashion. Question? If not, let's move on to, this is supposed to be lecture 3, but we can cover some of it now. Two last points, and we're gonna switch to matrices, and I wanna talk about 2 points about symmetric matrices, which are gonna be very useful. And this is itself requires like maybe a separate course actually to talk about, but just a couple of lectures, but I'm going to do it in like 15 minutes. So brace yourself. So A is like a matrix, which is symmetric, like n by n. And symmetric here means A is equal to A transpose, right? So for example, if I have a matrix like this, is this symmetric? No. This one is symmetric. So the off diagonals have to be like, if you mirror along the diagonal, it should be the same. So this fact that I'm going to talk about is about symmetric matrices, and it's called the eigenvalue decomposition. Okay. So what it means is, or what it says is that the matrix can be written as this decomposition, the product of three factors or three matrices. A matrix U, a matrix lambda, lambda is in the middle, and the first matrix, which is U transpose, okay? U lambda, U transpose. What is U? U is an orthogonal matrix. What is lambda? Lambda is a diagonal matrix. So what is an orthogonal matrix? An orthogonal matrix is a matrix that satisfies this identity. U transpose is equal to U transpose U is equal to identity. What is a diagonal matrix? Hopefully you know. So lambda is diagonal. And then I write it like this. Diagonal of lambda 1 up to lambda n, it means I have lambda 1 up to lambda n on the diagonal. And so there is that. Okay. So how many people have seen like orthogonal matrices? Okay. 1%. I hope you have seen diagonal matrices at the 2%. 3%. Okay, good. So like an orthogonal matrix is by definition like this. In other words, U transpose is the inverse of U. Okay, if you expand this, it tells you a very interesting story. So if I have U, which is the first column is U1, the second column is U2 up to UN. These are the columns, each is n by 1. So ui is in Rn, for I from 1 to n. I can do like a block matrix multiplication. So let's say we look at this U transpose U equal I. That's the kind of interesting part for us. So you do U transpose U. I can transpose U like this. So I transpose the first column, I get U1 transpose. It's going to be a row. And then U2 transpose, another row. And all the way to UN transpose, another row. Okay, so this is n by n, but written in like a blockwise format, and then multiplied by this U1, U2, UN, and you can verify that you can multiply as if you're multiplying like scalars. So the first coordinate, the first element would be basically U1 transpose U1. And the second element would be U1 transpose U2, and so on. So I get U1 transpose U1, U1 transpose U2, all the way to U1 transpose UN. Here I get UN transpose U1. U2 transpose U1 here, U2 transpose U2 all the way, U2 transpose UN, and then UN transpose U1, UN transpose U2, all the way to UN transpose UN. Okay, so now do you recognize these quantities? What are they? Like what is U1 transpose? Let's say what is this quantity? U1 transpose, yes.
It's the inner product.
It's the inner product, okay, good. So this is U1, U2 inner product. And so the claim is that this matrix is equal to identity, which means that all the off-diagonal elements are 0. So this is going to be 0, and every other one of these would be 0. So what this means is that all these vectors are pairwise orthogonal. Okay, so like a orthogonal matrix has this property that every pair of columns are orthogonal to each other. So ui is perpendicular to uj if I is not equal to j. So what happens if I is equal to j? On the diagonal, because it's equal to the identity, and diagonals we have ones. So basically ui transpose ui is 1, which happens to be the norm of ui squared. So in other words, the norm of ui is 1. Okay, so these are called unit vectors. So every column is a unit vector or norm 1, and then the columns are orthogonal to each other. Okay, so I had a little exercise in the first lecture about a set of vectors that are pairwise orthogonal, and none of them is 0. So none of these can be 0 because the norm is 1. 0 vector is norm 0. So you don't have 0 in the set, and they're pairwise orthogonal. You remember that little exercise? What can we conclude about the set of columns?
Describe them again.
Sorry?
I said describe them again.
Okay, so you have a set of vectors that are pairwise orthogonal and don't contain 0, so the 0 is not in the set. So what can you say about that set? Linear independent, okay, yes. That was the little exercise. So now you can go back, so now that you know the definition of inner product, orthogonality is like inner product 0. Try to prove that statement. And here we have this property. So the columns satisfy this, so they form a linear independent set. Okay, and because we have n of them, so if you have in Rn you have n linear independent set, a set of linear independent vectors, they form a basis because you can't have more linear independent sets, so they span the whole thing. So this set of columns end up being a basis for Rn. And because they're orthogonal and they have unit norm, we call them orthonormal basis. So it's an orthonormal basis. Okay. So where do they come from? What are the relations with A? The relation turns out to be, so every matrix defines this kind of decomposition. So it produces a particular orthonormal basis for the space, which is very useful. And Where do they come from? So what are the lambdas and the u's? Anyone has seen this in linear algebra? If I give you a matrix, how can you compute this decomposition? No one has seen this. So these UIs together, so they're paired with lambda I. So lambda i's are the diagonal elements of lambda. So the pair with H, which I don't want to do. This has changed. Yeah, forget about it. I'm gonna do it here. So lambda I and VI, or say UI, each one is an eigenpair. So lambda I is an eigenvalue of A, and UI is the corresponding eigenvector. That's why it's called eigenvalue decomposition. So people have seen eigenvalues and eigenvectors. How many people have seen eigenvalues? Okay. So now that a lot of you have seen what is an eigenvalue, let's see. Yes.
It's basically a scalar value.
Eigenvalue is scalar value, but it has more interesting property, not any scalar. So what does it have to do with the matrix?
It's basically scalar values that can be, so you can scale every associated eigenvector and there's some binary.
You can scale every associated eigenvector, and then what happens that
Or so binary.
they are linearly independent. Yeah, so that statement, I'm not sure if it's necessarily true or false, but there's a defining property. So what is the relation with the matrix? So these are eigenvalues and eigenvectors of a matrix. So what do they have to do with the? We'll get to it, but why do we call them eigenvalues of the matrix, for example, eigenvectors of the matrix? Okay, so what was your idea?
For any eigenvector, if we take A or A and B, it goes to lambda I. Yeah.
Okay, so let's say lambda u would be an eigenpair if A times u is lambda u. Is that okay? Yes. So this is the definition of an eigenvector. So eigenvector would be a non-zero vector such that when I multiply A by u, I get a scale multiple of u. Okay. So that scalar would be called the eigenvalue. So what does it mean? Let's say in R2, if I have a vector, let's say A is 2 by 2. Right? For example, I have 1, 2, 2, 1. And if I multiply, let's say 1, 1, multiply by 1, 1, what do I get? Three times 1, 1. Okay. So this would be an eigenvector because I can write it as like AU is 3U, and this 3 would be the eigenvalue. So what if you think of the A as an operator, as I mentioned? Yeah, give me a sec. If you do it, think of it as an operator, it takes elements because the input and output are the same. It takes elements from the input space and maps them to like every U is mapped to a U. And the eigenvectors are special in that they're mapped in the same direction. So it doesn't change the direction of these vectors, it just scales them along that direction. So if this is, for example, 1, 1, this matrix just maps it to 3, 1, 1. Okay, it doesn't change the direction. Other vectors that don't have this property. Okay, so what was your question?
No, I was gonna say, so you can basically just define every vector in the space as scalar multiples of the space's vectors by diagonalizing.
Okay, so you can write every vector in the space as a linear combination of the basis vectors. Yes. Diagonalize it is a property of the matrix. So this, okay, they're interesting questions, or like points. There are 2 points. Okay, so every vector in the space can be written as a linear combination of the basis vectors. And a matrix, like a symmetric matrix, can be diagonalized. Diagonalized means this. So I can write its decomposition where the middle matrix is diagonal. So why this is interesting? Because now putting the points together, because these are an orthonormal basis, so UIs are form an orthonormal basis, I can write every vector as a linear combination of this. So if you give me a vector, I wish I could open a new page to change the, how do we get a page? Yeah, forget about it. I'm gonna do it very compactly here. So you do, maybe we have some room here. So if I have an x, I can write it as like alpha I ui. Okay, for every x, there is an expansion in terms of the basis vector uniquely. So these alphas would depend on x. And then when I apply a to x, what would happen, because a is a linear operator, or it just passes through this, you get I from 1 to n, and you get like basically a times alpha I ui, and then just because again a is a linear operator, alpha I comes out, you get a times ui, but a times ui is what? Oh, I didn't mention, or didn't mention. So because they're eigenpairs, so I have a ui is lambda I ui. That is what it means. So for each ui, when I multiply a by a, I get lambda I ui. That's what it means for ui and lambda I being an eigenpair of a. So this would be lambda I ui. Okay? And you notice something very interesting. So you started from this, and then we got that ax is equal to summation alpha I lambda I ui. Okay? So we can describe the action of A on any vector by just computing these quantities, because this is the expansion. And you can see this is the expansion of x in U in terms of the basis, and this is the expansion of AX in terms of the basis. So these are the new coefficients. Okay, and these coefficients are basically, if you think of a matrix which is lambda, the diagonal matrix, if you multiply it by alpha 1 up to alpha n, okay, you get these coefficients. You get lambda 1, alpha 1 up to lambda n, alpha n. So we turn the action of the matrix into the action of the diagonal matrix. So if you give me a diagonal matrix, I can easily compute what it does to a vector. So the effect of this eigenvalue decomposition is that I can now tell you this operator how it acts on x by expanding it in the orthonormal basis of eigenvectors, and I just look at those coefficients, and on those coefficients, the A acts like a diagonal matrix. Okay, those directions are just, this is how each direction is multiplied, and so you just expand in those directions. So basically, you decompose into those directions you scale, and then put them back together. So on that, in that basis, the matrix looks like a diagonal matrix. That's what diagonalization means. Okay, and this is like compactly represented here. So what happens is when I do this multiplied by x, you can verify that this is really computing those alphas. So these alphas are really. Basically, the alpha here would be U transpose X. So this maps it to the basis. So this represents the vector into the basis defined by U. This is the action. So I'll like you get U lambda alpha. This part is the action of that diagonal operator on alpha. And then let's call this beta. And then you put it back together. So this U beta would be just summation beta I ui. Okay. So what it does is like this very short, linear algebra is nice because like a single identity has a lot of information. So this is like, if you understand it geometrically, when you multiply A by X, you first translate X to the basis, which is described by the orthonormal basis of the eigenvector. So that's this part, U transpose X. then you act on it as a diagonal matrix, which is lambda times that alpha, and then you put it back in the original kind of domain, which is like U times or the original kind of basis. This puts it back. So it's really a change of basis. And then once you do the change of basis, the matrix looks like a diagonal matrix. Again, a lot of geometry and intuition and information. So that's why eigenpairs are important, and that's why this decomposition is important. Is that clear? That was a lot of information that I wasn't prepared to talk about, but good point. So what was your name, by the way?
Bollock.
Balak. Okay. Good question. Yes.
So geometry is U a rotation matrix?
That's a whole interesting story. Yes, and a little bit more. Could be like reflection as well. Yes, maybe more. Yeah. So they don't. Okay, you're asking very good questions. So you can prove that U times X, the norm is the same as norm of U. We can expand it. If you do a square, you can prove it. So they leave the norm of vectors the same. So then they leave the distance as the same. Because then if this is true, then U times X minus Y is the same as X minus Y. And this is really norm of Ux minus Uy. So if you apply U to two vectors, the distances remain the same. And because the norm remains the same, and then you can write the inner product in terms of norm using the what is called polarization identity, that the inner product is the same. So Ux and Uy. It's also you can directly show. So inner products remain the same under the action of U, and so the angles remain the same. So the geometry remains the same. So rotation is an example, reflection is an example. I'm not sure if that's the only thing, but that's kind of roughly what happens. Okay. Yes. Another question? These are special transformations. Okay, I think this is good enough. A lot of information. Actually, not just one more. Good enough for that slide. Just one more thing. So these are two examples. You have 1 minute. You can go through and verify. For example, this was the matrix. We verified that 1, 1 was an eigenvector associated with eigenvalue 3. So this is like 3, and this is the vector eigenvector normalized. Once you normalize to unit norm, that would be that. And then this is the second eigenvalue, this is the second eigenvector. And so when you do the eigen decomposition, this would be the two eigenvectors put on the columns, and then you get the eigenvalues in the middle. And so you get U lambda U transpose. For the second matrix, you do the same, calculate the eigenvalues turn out to be 2 and 0. And this is going to be the first eigenvector associated with that, the second eigenvector associated with this. And the interesting thing is now you can, for example, read the rank of the matrix of this diagonal part. So what is the rank of this matrix? The rank of this would be 2 because the two are linearly independent, and you can see here the eigenvalues are both non-zero. The rank of this would be the same as the rank of this. What is the rank of this matrix? 1, because one column is the multiple of the other, and you can read it here as well. So one of the eigenvalues is 0. Once you have a 0 eigenvalue, you drop one of the ranks. So the number of non-zero eigenvalues would be the same as the rank. And this, you can see also it's a rank 1 matrix because the 0 this one can't be in a basis. So the rank of this is the same as the rank of this. So basically this decomposition gives you the rank easily and more information as we've seen. Just verify these for yourself. Go back, read about eigenvalue, eigenvectors, try to compute all the eigenvectors, eigenvalues, and verify this decomposition. Okay. Thank you. I will see you next week.